Good morning, everyone. Welcome to today's presentation. I'm excited to introduce our topic, Introduction to Deep Learning. Today, we'll explore what deep learning is, how it works, and why it's so important in the field of artificial intelligence. We'll cover key concepts, some real-world applications, and future trends. But first, let's get started and dive into this fascinating subject. Let's talk about creating algorithms that can really understand scenes and describe them in natural language. The goal here is to enable machines not just to see an image, but to interpret what's happening and explain it clearly. These algorithms also need to infer semantic concepts, which means they should understand the meaning behind what they see. This allows machines to interact with humans more naturally, using concepts that make sense to us. Achieving this requires building a series of abstractions. We start with raw pixel intensities in an image, then move to identifying objects within that image, understanding relationships between those objects, and finally, generating a scene description. Deep learning is key here because it aims to automatically learn these abstractions with minimal supervision. Instead of explicitly programming every step, deep learning models discover the patterns and concepts on their own, which makes them powerful tools for scene understanding. A motivational way to think about this is how we go from percepts, what we perceive visually, to concepts, what those percepts mean. This progression from raw data to meaningful understanding is at the heart of creating intelligent, perceptive machines. On this slide, we see a series of example image descriptions that highlight how computers can interpret visual scenes. The first description talks about a construction worker in an orange safety vest working on the road. This illustrates how detailed and specific these descriptions can be, capturing the worker's attire and activity. Next, we have a man in a black shirt playing guitar, showing how actions and objects are recognized and described accurately. Then, there are two young girls playing with a Lego toy, emphasizing the system's ability to identify multiple subjects and their interaction. Finally, a boy is doing a backflip on a wakeboard, which demonstrates how dynamic actions and motion are also captured effectively. These examples are part of the broader theme of deep visual semantic alignments, which aim to teach computers how to generate meaningful, natural language descriptions of images. This is a key step toward bridging visual understanding with language, making machines better at interpreting and explaining what they see. When we look at modeling complex behavior, we quickly realize there are many challenges. First, there are simply too many concepts to learn all at once. Then, we have a wide variety of object categories that we need to understand and distinguish. On top of that, the ways in which these objects can interact are incredibly diverse, adding another layer of complexity. Behavior itself is highly variable, influenced by many underlying factors that are often hidden or latent. We can think of this as a function, which we can denote as f, that maps these latent factors, L, to observable behavior, v the latent factors, L exist in a low-dimensional space, meaning there are fewer underlying causes than the behaviors we observe. Meanwhile, the visible behavior, v, exists in a high-dimensional observable space, reflecting all the different possible outcomes and actions we can see. Now, this mapping, f, is highly nonlinear. That means small changes in the latent factors can lead to big, unpredictable changes in the observed behavior. This nonlinearity makes modeling and predicting behavior especially challenging. So overall, the key challenge in modeling complex behavior lies in managing this gap between the simple, low-dimensional causes and the complex, high-dimensional observable outcomes. It's about understanding how these hidden factors influence what we see, which is no easy task. Let's take a closer look at this example, learning the configuration space of a robotic arm. Now, the configuration space essentially represents all the possible positions and orientations that the robot can achieve. When we're studying this space, we're trying to understand how the arm can move and what constraints might exist. This is really important because it helps us plan motions that are efficient and collision-free. By exploring the configuration space, we gain insights into the robot's capabilities and limitations. This example ties directly into the overall theme of understanding complex systems and how to effectively navigate their possible states. It highlights the importance of mapping out these spaces to enable better control and planning in robotics. Now, let's explore how we can discover the structure of C-space using IsoMap. IsoMap is a powerful nonlinear dimensionality reduction technique that helps us understand the true shape of high-dimensional data. Essentially, it works by preserving the geodesic distances between points, which are the shortest paths along the manifold itself, rather than straight-line Euclidean distances. This is especially useful when dealing with complex, curved spaces like C-space, where traditional methods might fail to capture the true structure. By applying IsoMap, we can generate a lower dimensional representation that retains the essential features of the original space. This allows us to visualize and analyze the connectivity between different configurations more intuitively. Overall, using IsoMap in C-space discovery helps us uncover the underlying geometry, making it easier to identify feasible paths and understand the robot's capabilities within its environment. This step is crucial for planning and motion analysis, connecting directly to the broader theme of efficient, intelligent robotics navigation. Let's talk about how inspiration from the mammal brain has shaped our approach to training deep neural networks. As you can see, these models are built with multiple layers of neurons, much like the layers in a biological brain, a concept discussed by Rumelhart and colleagues back in 1986. The idea is to train each layer to build on the representations learned by the previous one. This way, each layer gradually learns to recognize more complex features, moving from simple pixels to more abstract concepts like object parts and categories. For example, early layers might detect edges, then contours, then specific parts of an object, and finally, the entire object category. This layered approach allows us to capture both local features, like edges, and global features, like the overall shape of an object. To make this work efficiently, we typically train the layers one at a time, a method known as greedy training, which was proposed by Hinton and his team in 2006. By training layer by layer, we simplify what could be a very complex optimization problem into manageable steps. This incremental process helps the network learn meaningful hierarchical representations, enabling us to build powerful deep architectures capable of complex tasks. Let's take a closer look at how the learning process works in a multi-layer perceptron with backpropagation. First, the model compares its outputs with the correct answers to generate an error signal. This error signal is crucial because it tells us how far off our predictions are from the true values. Next, we backpropagate this error through the network. This means we send the error backward from the output layer to the hidden layers, calculating the derivatives needed to adjust the weights. Essentially, we're figuring out how each weight contributed to the error, so we can update them accordingly. This process of comparing, calculating errors, and updating weights is fundamental because it allows the network to learn from its mistakes and improve over time. It's a key concept that underpins the entire field of deep learning and neural network training, connecting back to the very first models like the multi-layer perceptron introduced by Rumelhart, Hinton, and Williams in 1986. They are discriminative models, which means they focus on getting all the information from the labels of the data. But here's the thing, these labels don't always provide a lot of detailed information on their own. That's why we often need a substantial amount of labeled data to train these models effectively. Now, when we talk about training neural networks, a common approach is gradient descent, starting from a random initialization. The problem with that is it can lead us to poor local minima, points where the model gets stuck and doesn't find the best possible solution. This highlights some of the drawbacks of backpropagation-based deep neural networks. While powerful, they can be quite sensitive to initialization and require large amounts of labeled data to perform well. Understanding these challenges helps us appreciate the ongoing efforts to improve training methods and develop more robust models. Let's take a closer look at the classification of MNIST handwritten digits. As you can see, there are 10-digit classes, representing the numbers 0 through 9. The input images are 28 by 28 pixels, and these are grayscale images, meaning each pixel has a single intensity value. When we flatten these images into a vector, that gives us a 784-dimensional input, since 28 times 28 equals 784. This high-dimensional space is what our models will operate on to recognize handwritten digits. The core goal here is handwritten digit recognition, which is a classic problem in machine learning and pattern recognition. It serves as a great example to understand how we can build models to interpret and classify visual data effectively. Let's take a closer look at what a single hidden layer with 500 neurons actually involves. Essentially, we're talking about connecting 784 input features to these 500 neurons, which means we have 784 times 500 weights, plus an additional 500 weights for the biases. Then, these 500 neurons connect to the output layer with 10 classes, adding another 500 times 10 weights. When you do the math, that totals roughly 0.4 million weights that the model needs to learn. Now, fitting a model of this size, that is, finding the best weights to explain the training data, is really an optimization challenge in a 0.4 million dimensional space. It's a huge, complex landscape to navigate. And here's the key point. It's almost impossible for gradient descent, especially starting from a random initialization, to reliably find the global optimum in such a vast space. This is why training deep neural networks is such a fascinating and difficult problem. It highlights the importance of understanding why optimization is so challenging, and how our methods must be designed to effectively explore these enormous, high-dimensional spaces. So here we see that working with very high-dimensional parameter spaces can be quite challenging. When we start training a neural network, we typically initialize it at a random position in this complex landscape. From there, the backpropagation process begins, but it tends to be very slow, especially in these high dimensions. Often, this slow process causes us to get stuck in poor local minima, which means the network settles on suboptimal solutions that don't really solve the problem effectively. Then, we might try fine-tuning the network using backpropagation again, but that can be slow and may not always lead us to the best possible solution. This is where the idea of a good, initial solution becomes crucial. If we can find a way to start closer to a good point in the parameter space, we can significantly speed up the training process and improve the final outcome. One effective approach is fast, unsupervised pre-training. A notable example of this is deep belief networks, introduced by Hinton and colleagues in 2006. They use layer-by-layer pre-training to initialize the weights of the network in a smart way. This pre-trained network, then, provides a much better starting point for supervised fine-tuning, leading to improved performance and faster convergence overall. Before applying backpropagation, it's often beneficial to first pre-train the network as a series of generative models. This means we start by training each layer to model the data in a generative way, which helps the network learn useful features early on. By doing this, we can use the weights from this pre-trained network as the initial point for the traditional backpropagation process. This approach actually leads to quicker convergence, meaning the network reaches a good solution faster. It's a way to jumpstart the training process and avoid some of the difficulties that come with training deep networks from scratch. However, it's important to note that while pre-training is typically fast, fine-tuning the entire network afterward can sometimes be slow. That's where the concept of deep belief networks comes in, as proposed by Hinton and his colleagues in 2006. Deep belief networks offer a structured way to pre-train deep networks efficiently, making the overall training process more manageable and effective. So, in essence, pre-training sets a strong foundation that makes the subsequent fine-tuning more efficient and ultimately improves the network's performance. Let's take a closer look at the performance comparison between the multi-layer perceptron, or MLP, and the deep belief network, or DBN, on the MNIST dataset. Starting with the hardware, We're working with an Intel quad-core processor at 283 GHz and 4 GB of RAM, which provides a solid baseline for running these models. For the MLP, which has just one hidden layer, we see that after 1 hour, the error rate is around 2.18%. If we extend the training to 14 hours, the error drops to approximately 1.65%. This shows that longer training improves performance, but with diminishing returns over time. Now, looking at the DBN, the results are even more promising. After just 1 hour, the error rate is about 1.65%, matching the longer training time for the MLP. Extending training to 14 hours reduces the error to around 1.1%, and at 21 hours, it further decreases to roughly 0.97%. This quick check highlights a key point. DBNs tend to converge faster and achieve lower error rates with similar or even less training time compared to MLPs. This demonstrates their efficiency and potential for better feature extraction. Overall, these results reinforce the theme that model choice and training duration have significant impacts on performance, and that deep architectures like DBNs can offer substantial advantages in terms of accuracy and training efficiency on datasets like MNIST. Let's talk about distributed representation and how it contrasts with localized and sparse representations. In distributed representations, each neuron encodes multiple features, and combinations of neurons represent complex information. Interestingly, only about 1 to 4% of neurons are active at any given time, making the system quite efficient. The activation of each neuron depends on multiple features from the previous layer, meaning that neurons are responsive to various aspects of the input. This allows for rich, flexible representations. Also, it's important to note that feature combinations across different neurons aren't necessarily mutually exclusive. They can overlap and interact, which adds to the robustness of the system. This approach helps us understand how the brain disentangles the underlying factors of variation in data, allowing us to interpret complex information more effectively. In the context of brain function, these intermediate representations serve as a bridge between raw sensory input and higher-level cognition. Overall, this interconnected, distributed approach is key to understanding both artificial and biological neural systems, as it balances efficiency with a capacity for complex, nuanced representations. Now, let's talk about local methods. These approaches assume a smoothness prior, meaning that nearby points in the input space tend to have similar outputs. Specifically, we can think of a function g of x, which is defined based on the values of g at neighboring points, like g, x1, g, x2, all the way up to g, xk. Where these points are neighbors of x to make this work, we typically require a metric space, which means we need a way to measure distance or similarity between points in the input space. However, it's important to remember that these local methods can fail when the target function changes very rapidly. That is, when the function isn't smooth at all. Some common examples include nearest neighbor methods and kernel methods that use a Gaussian kernel. These techniques rely heavily on the idea of local similarity. On the other hand, there are distributed methods, like neural networks, which don't make the assumption of smoothness. They don't need a notion of distance or similarity in the input space, allowing them to model highly complex and varying functions. Finally, it's useful to compare local versus distributed approaches in the input space. Local methods focus on small neighborhoods, while distributed methods consider the entire input space more globally. Each has its strengths and weaknesses, and choosing between them depends on the nature of the problem you're tackling. Now, let's take a closer look at multitask learning, which is a fascinating approach in machine learning. Essentially, multitask learning involves training a model to perform several related tasks simultaneously. By doing so, the model can leverage shared information across tasks, which often leads to better performance compared to training separate models for each task. This concept is particularly powerful because it encourages the model to develop more generalizable features, capturing underlying patterns that are useful across different tasks. It's like teaching a student multiple related skills at once, often. Understanding in one area enhances learning in another. Connecting this to our overall theme, multitask learning exemplifies how integrating related objectives can improve efficiency and effectiveness in machine learning systems. It's a strategy that not only saves resources, but also boosts the robustness of the models we develop. Now, let's talk about some of the key abilities we want our AI systems to develop. First, the ability to learn complex and highly varying functions. This means they can adapt to a wide range of tasks and data patterns, even when things are very different from what they've seen before. Next is the ability to learn multiple levels of abstraction with minimal human input. Essentially, AI should be able to build layered understanding on its own, reducing the need for constant supervision. Another crucial point is learning from a very large set of examples. The more data we provide, the better the system can generalize and perform well in real-world situations. Interestingly, the training time should be linear in the number of examples, meaning that doubling the data shouldn't cause exponential increases in training time. That's important for scalability. We also want AI to learn from mostly unlabeled data, which is abundant and easier to collect than labeled data. This involves approaches like unsupervised and semi-supervised learning, allowing systems to discover patterns without relying solely on manually annotated datasets. Multitask learning is another vital aspect, where the AI learns to handle multiple tasks simultaneously, sharing representations across different problems. This not only improves efficiency, but also helps the system develop more robust, generalizable knowledge. Finally, we desire fast predictions. Once trained, the AI should be able to deliver results quickly, making it practical for real-time applications. All these capabilities are essential desiderata, key goals, for developing truly intelligent AI systems that can adapt, learn efficiently, and operate effectively across many different scenarios.